So in figure 8-7, we have WaveGen. So that we are going to use the yellow wire from the analog discovery to set up or configure WaveGen. And as you know, WaveGen simply goes from +5 to -5. That's going to be the limiting voltage for WaveGen. So if you want to explore more voltages or a bigger range of voltage, we are going to have to use a DC offset for that. So we are setting it up using this negative power supply on this side. So the maximum voltage over here on WaveGen is going to be +5 with respect to ground, but with respect to V minus, it is going to be much higher. So for example, if I set V minus to be -5, the +5 voltage is going to be essentially +10 with respect to V minus. So I'll be able to explore a bigger region of the voltages, which is why I am going to connect the white wire, which is our negative power supply, to this end. Um, they are they are grounded internally. So the reference voltage, which is the ground voltage for all these voltages from WaveGen and V minus, all those are internally referenced to the analog discovery. And clearly all these things are mentioned in the write-up, but I'm going over them quickly over here. Um, in the circuit, we have two components. One is a resistor R1, which is 1 kilo ohm. So that's brown, black, red resistor over there. And then we have another component D1, which is the 1N4148. So it looks like a orangish small little two-terminal component, and I encourage you to look at the data sheet for 1N4148 to look at how it looks like. But it's an orange tinge inside there, clear casing. On one of its sides there is a black circle on one of its ends, indicating that it is the cathode or the negative side. Right now it is pointing down, the way I've set it up. So I've got the resistor connected to the cathode and the negative terminal going to the white wire here, which is I'm going to connect to the negative power supply. So very simple, not too many connections, two components. I have put two orange wires across the diode to indicate that I will be measuring uh, channel 1 voltages for the diode, and channel 2 is connected across the resistor R1, which in this case is the current sensing resistor. And I'm providing a WaveGen and V minus using the yellow and the white wire. So what I can quickly do is make those connections from the analog discovery and start waveforms. So I've got this guy here, white connected to white. Let's see, blue on this side connected to blue, and blue stripe connected to the other end of the resistor. Notice usually our blue stripe and orange stripe wires are connected to ground. In this case, it's going to be a differential voltage measurement. So it's going to be on the other side of the resistor. Orange stripe is connected to the cathode of diode, and orange is should be connected to the anode of the diode. And then finally, okay, I already connected V minus. So I've made all the connections here to the analog discovery. I think we'll find out if I missed some. Um, so what I'll do is I will have this window on the side here, and we can make this waveforms window bigger, and we can start setting up our do we need scope? Absolutely. Do we need WaveGen? Yes. Do we need voltage supplies? Yes. We don't need the positive one. We definitely need the negative one. And in the write-up, um on page On the next page, so if you look at page 6, if you guys have it, on page 6, we are asked to set the power supply to -4. So I'm going to go make it -4 volts here, and it is ready to be turned on. I will go to WaveGen. We are asked to select a triangle wave with a frequency of 1 kilohertz and an amplitude of 5 volts. All right, I think that's it. 5 volts, 1 kilohertz. Yes, yes, yes. So I can turn on supplies now. I can turn on WaveGen now, and they're both running. I can go to scope and start my. But before I do that, let me give you a sense of how we should go about this. The WaveGen was set up at 1 kilohertz. So that means one time period is going to be 1 millisecond. And if I want to take a look at, for example, two time periods, then my time scale should be completely 2 milliseconds. The x-axis should be 2 milliseconds. And 2 milliseconds divided in 10 divisions, that results in uh, zero point 0.2 milliseconds per division, or 200 microseconds per division. So without even like trying to figure it out, um, by hit and error, trial and error, I'm just fixing the base of my measurement to 200 microseconds per division, uh, and I'm going to expect two time periods of my waveform by doing that. The range, I'm going to make it 2 volts per division on both channel 1 and channel 2, so that I can see the entire thing. Let's see. If I run it now, clearly I see two time periods. So my estimate on the time period was pretty accurate. And I also see the voltage on channel 1, which is the diode here. And as you can see, it is getting limited to 0.7. Perhaps if I make this a little bit thicker, you can see that the orange line is the voltage across the diode. The blue line is the voltage across the resistor. Uh, so I hope now all the theory that we learned a few minutes ago, now you are able to see that play out. So this is limited to 0.7, but the negative half cycle follows the source, and then you are getting that. So that's going to be your um, channel 1 versus channel 2. So that's voltage across the diode and the voltage across the resistor, and we are seeing both of them uh, being displayed over here. Now let's see, our goal for part A is to sketch the current voltage characteristics of this diode. And clearly, we don't have the current yet. We have the voltage across the diode in the form of channel 1, but we don't have the current through the diode. So to get the current through the diode, what we can do is we can add a math channel. So in this add channel, I'm going to add a custom math channel here, and I'm going to change the math for this channel to be C2, because that's my voltage across the resistor. And if I can divide that by 1000, because it's a 1 kilo ohm resistor, then I can measure the current. So C2 divided by 1000. Why C2? Because that's what is the voltage across the resistor. Why 1000? Because the value of the resistor is 1 kilo ohm. And I'm also going to change the units to amps, for example. And then I will say OK. So once I do that, I get a red line over here, which is very, very tiny because it's in the milliamp region. So to see exactly what's going on, I'm going to disable channel 1 and 2, and then change the range of my math channel to 20 milliamps per division. In fact, I can go a little bit more. Uh, 5 milliamps per division, 2 milliamps per division. Now you guys can see the current through the resistor that we have obtained by using a math channel. We of course have the other two channels as well over here, C1 and C2. And I hope you saw that when I turned on C2, it landed on top of the math channel, because all we are doing is channel 2 divided by 1000, we get math channel 1. So if this guy is 2 volts per division and if this is 2 milliamps per division, they are going to exactly be on top of each other. Um, so now we have the voltage across the diode in the form of the orange line, or the channel 1. We have the current through the diode in the form of a math channel. So I believe we have both the measurements, simultaneous measurements, so we should be able to sketch the current voltage characteristic. But before I export this into a form of a file, what I'm going to do is I'm going to check whether this actually works. Um, there is a way to do this directly in analog discovery, and I will show you that in just a moment. So what I'll do is I will click on view and I will say add XY, and in this add XY, again I will try to increase this on to 3, perhaps 4 is better. And on x-axis I have C1, on y-axis I have C2. What I desire is, on x-axis I need voltage across the diode, and C1 is voltage across the diode, so that's good. But on y-axis I need current through the diode, which should be set to the math channel. So I'm going to change that to the math channel, and I'm done. And if I see this, it looks exactly the same as what we had observed in the theory. So beyond 0.7 volts, it shoots up, and on the negative side, when it is reverse bias, it is close to zero. Very, very small saturation current flows through. So based on how it looks over here, I am satisfied with how it is going to look like when I export these numbers to Matlab, for example. Um, so that's one quick way of checking it before you actually export the data. I don't need this right now, so I'm going to make this smaller, and I'm going to get this back on. And let's say I can stop this measurement for now, and I can do file, export the data. So the data, I'm going to get 1, 2, 3, 4 columns. First column is time, second column is channel 1 voltage, which is the diode voltage, channel 2 is the resistor voltage, and the last column over here is the current through the diode. In fact, I could have done the math channel, the current through the diode in Matlab, by taking channel 1 voltage and dividing it by 1000 in Matlab. But I've done it over here. Anyway, so I'll save this data, and it's going to ask me to save it to some place. So let's see, in experiment 8, let's see, new folder, experiment 8, done and done. And over here I will say IV characteristics, and I will perhaps name them a little bit differently later. So I've got, actually, you know what, just to keep it simple, I will just call it data.csv, and then I will save it over here. And if you go check in your file folder, you should be able to see that. So that's as far as getting the data from the analog discovery is concerned to sketch the IV characteristic. Now I'm going to minimize these windows, and I'm going to bring up my Matlab window here, and I hope you guys have been you have worked on uh, getting the Matlab installed on your computers, and uh, because you are going to have to work on generating the results. I'll just walk you through how to do it, but you guys are going to individually have to work on this. So I will only be able to share the data, the CSV file with you. All right, so um, I'm going to stop the protoboard view for now, and then I will be able to start typing up the commands that we are going to need to actually do the experiment, to do the MATLAB portion. So to help you, uh, the write-up already has the MATLAB code. So if you see over here, there's a lot of MATLAB code that will help us with this. So to save time, I'm going to copy this and paste it in my MATLAB window. And for those of you who are new, let me quickly walk you through some of the things. So when you start MATLAB, you will see on the left there is a current folder window. This is essentially showing you all the contents of the current working directory. At the bottom over here, this is the command window where it gives you a prompt for you to be able to type in simple commands. So if you have one or two uh, commands to execute, then you can type them in to the command window. But in our case, we have a bunch of commands to execute at once. So we are going to actually write a MATLAB script, which has the extension of .m. So that's what I'm doing right here. I'm writing in the editor, MATLAB editor, I'm typing in all the commands so that I can execute all those commands at once. On the right, there are two windows. One is command history, and that is just showing me the history of the commands that I typed in into my command window. And there is Workspace, which is going to show me when I run the MATLAB code, it is going to show me the variables that uh, I will be using during that program appear over here. So their size, their contents, all of that I can monitor in the Workspace. So that's a quick review of this. On Piazza, I have put up a couple of very useful resources. So if you're new to MATLAB, please take a look at that to kind of get a head start on a good start on what MATLAB is and get familiarity with the interface. So um, uh, let's see, what am I doing here? I'm copying the code for now. So I've copied a few lines, then I'm going to go down and I'm going to copy more lines. I'm going to have to adjust all these lines. I'm going to have to change these statements based on what I have. But for now, I have literally done a copy paste for the MATLAB code that was provided in the write-up. Um, Now I'm going to import the data file. And the way I can import the data file is if I say open, actually, no, I don't need open. Let's see, untitled. Okay, so let's see, where is import? If I go to home, there is an import data option in the home menu. I will click on that. Once I click on that, I will be getting the date, so I can point to the data file now. Once I do that, it should show me another window with how I want to import it. Okay, once I do that, it comes up with this window and it says, okay, these are the things that you want me to import. Do you want me to make any changes? So I think I will make some changes. So I will call this time for the first column. I will call this guy channel 1, I believe was the voltage across the diode, so I'll simply call it VD. Channel 2 was the voltage across the resistor, so I'll call it VR. And the math channel was the current through the diode and the resistor, so I'll call this ID. And it is highlighting all the values that are being imported. and I want to import them as um, a matrix. So I'll select numeric matrix here, um, and let's see, the range is specified, all of these, and then I'm going to do import selection. And once I do the import selection, I believe I should be able to see right there. So if you see here, data, it appears in my workspace because I just imported it um, as a matrix which has 8,192 rows and 4 columns. Each of those columns correspond to uh, time, VD, VR, and ID. Um, Actually, in my import, if I selected individual columns like column vectors, they would have appeared as 4 different things. But because I chose numeric matrix, it is showing me all at once in the same matrix. That's fine. So now I'm ready to actually go through this. So what I'll say is time equals, it's not untitled, it's now going to be data, and the first column, all the rows and the first column. So as you can see, the colon operator is suggesting that it is all the rows, and comma 1 indicates the first column. So time is data, all the rows, first column. Voltage across diode is data, all rows, second column. So that's good. Current through the diode is data, fourth column. I don't even need to do the divide by 1000 in this case because I already did that in waveforms. Plot VD versus ID, and the marker type is selected to be a dot. Then we apply hold on, meaning if I want to sketch more plots on top of this plot, then I will have to preserve or hold whatever I did earlier. So I'm going to preserve it so that whenever I put something new or plot something new, that doesn't go away. I do a hold on and I do a grid on. So that allows me to look at a grid on top of that. Uh, and then underneath that, I have a few equations. There is IS, which is the saturation current. There is N, which is a parameter zero, between zero, above zero. There is VD, there is ID. So VD is for voltage across the diode. We are scanning it from 0 to 5 volts in steps of 0.01 volts. And ID is a exponential function over here which has several parameters. There is IS, the saturation current. EXP is the exponential function. VD is the voltage across the diode. We are saying we want to evaluate ID for the voltages that are going from 0 to 5 in steps of 0.01. N is the value over here which we have set to 2. And then the remaining things are constants. You might be confused about the asterisk and the dot. So asterisk is just multiplication and the dot is element wise multiplication. So for example, if you had to divide a matrix or a vector by a vector, how would you do it? Well, it's not possible, right? So if you want to do a element wise division or element wise operation, then you choose a dot operator. So just before the value you have the dot. Just to make it clear, that's the number 0.0259. Anyway, so these two are analytical calculations for that particular exponential rise of the current through the diode as you increase the voltage across the diode. And we are also plotting that with a line width of 3 and in red color on top of the experimental data. So plot whatever you want on x-axis, whatever you want on the y-axis, and then several options for the plot command. The last statement over here is to fix the axis of the plot. The x min is 0, x max is 5, y min is 0, y max is 0.01. Well, let me just comment this, and I can comment that by doing a control R or adding a percentage sign in the front of the line. So I'll fix this later, but I believe right now I'm ready to run this. So what I'll do is I'll go to editor and then I will select run, and it's going to ask me to save the file. So I'll say in experiment 8, wherever that is, save it as IV characteristic. Probably not a good name here. IV underscore CHA dot M. Okay, and then I will save it. I already ran it. Yes, add to path. So hopefully when it runs, it should be able to give us the plot. And the plot that it came up with was this. Um, so there is a blue line in there, there is a red line in there. I'm not sure where things are starting and finishing. So what I'll do is I will actually go ahead and play with that access command, so to make this a little bit better view. And I will also add the X label, Y label, and say the title of the plot. So let me do that now. So for axis, say -2 to 6 would have been okay. And for the y-axis, -0.5 to yeah, I believe 1 is going to be sufficient. But let's see what happens. If I run this now, am I looking at a better plot? Okay. So it generated a plot for me over here. I'm going to use the zoom in command, zoom in tool here, so to kind of zoom into what is going on here. As you can see, this is the rise over here. This is going to be very tiny, so I will actually limit this to 0.01. And if I close this guy, where is that? Oh, that is still there. Run it. Mm. So right now I'm just playing with the access command so that I can get a better sense of how things should compare. I think this is a pretty good start. So on the blue line, we have this exponential rise, and that's for the experimental data. And for the red one, that's the um, theoretical relationship between current and voltage for the diode. And obviously, they are not overlapping. I can play with the parameters. The two parameters that I can adjust are the saturation current Is and the value of N. And as I change them, the red line is going to change. So for example, I can actually show you over here. So just to keep things simple, every time I run it, I want to close the figures to generate a new one. Let's see. My axis over here, -1 should have been good. And on the max, I believe 2 is probably good. um, Next, the thing that I'll do is run it. So when I run it, I should be able to see a better looking graph here. Now I want to ideally fit the theoretical curve to the experimental curve, so there's a quite a bit of distance between them. So I can change n. So for example, if I change n to say 1, what happens? I'm going to run it and I'm going to see that again. They are getting closer to each other. And in fact, you can tweak the parameters a bit more to actually get them to match up very, very well, to get a very good agreement between the experimental data and the um, theoretical data. So I will leave that sort of exercise to you, but hopefully I've shown you uh, how to, uh, you know, export the data from analog discovery, get it into Matlab, and run the Matlab code that is given to you on top of it. A few things to note over here. Um, well, let me show you how to add X label and Y label here. So X label is, let's say, we have voltage across diode, um, and Y label is current through diode in amps, and title is IV characteristics of 1N4148 diode. I will run it again, bring the graph here, and you can see your x-axis is now there, y-axis is there. I can actually, uh, tweak this more and more. I can keep refining my plot. I can also add a legend to suggest which one is experimental data and which one is the so you can do this as well. You can say legend. um, the first thing that we did was experimental data, so you can say experimental data, and then the second thing that we plotted was theoretical, so theoretical equation was the red one. And then you will start seeing the legend as well. um, so another quick little trick I will show you is, if you go to file, you can do export. When you do export, you can load a particular style. So for example, I like the presentation style a lot, so I can select presentations, I can load it and apply it to my figure. Once I apply it, you notice what happens to the figure window. It now looks very, very clear. And you can take this to your, you can do a edit copy figure and paste it into your Word document, for example. So all of that, if you play with it a little bit more, you will be able to figure out more and more things that make it appear very nice. But I guess this is a good start. Okay, so you're going to have to do this by yourself though. um, so I'll just share the CSV file. Okay, so I'm going to cross out of this and warn you about one thing that could happen. Notice when you imported the CSV file, it imported the data in the format double. That is exactly what you want, because if it is double, that means that whatever you write in your MATLAB script, you will be able to execute using that data in the double format. However, if it is in the table format, while you import the data, it may happen that you get it in the table format. If that is the case, if you get it in the table format, then you will have to actually, I will just show you how to do it if it is in the table format. So monitor the workspace. It should say double. If it doesn't, then you have to convert it to double format. So what you have to do is you have to say data equals table to array of data. So if data over here appears in the table format, then you're essentially saying use the function table to array, convert that table to a double format and put it back in the same variable data. So do that if when you import things, they appear in the table format. Right now we are good. We are in the double format, so we can do this. All right. So I hope that was helpful. I'm going to take a look at what, oh, we are over time. Okay. So for today, I guess this is it.